From Ampere's circuit law, it is stated that if we have a wire with a current going like that, if we were to position our thumb in the direction of that wire as such, there will be a magnetic field produced in the same direction as the curl of our fingers around that wire as such. If we look at our fingers, they move in that direction. Now, he also proved that there's a mathematical way to calculate the magnetic field produced by this wire around this, around the wire. This will be H dot dl is equal to I enclosed, which is Ampere's circuit law. Now the direction of this surface, or this line integral, follows the curl of our thumbs, and the I enclosed is in the direction of our pointer finger, which is up. This is from the right-hand rule. This is how we figure this out. Now, from this this relationship, we can derive the magnetic field around an infinite plane. So, if we were to look at just an x-plane, infinitely long, with charges coming out of the plane, defined by a surface current density. These are all currents coming out. Imagine lots of wires, infinitely many along this plane. Let's say it's K y is equal to negative. It has to be negative because, yeah, it has to be negative because it's the positive y direction is into the page, and these are all coming out. So this would be like negative, I don't know, whatever. Let's just say y. It's just some definition. Now, looking at each of these wires, they're going to produce a magnetic field in a counterclockwise direction as such, based on this rule I just told you. Now, if you look at them, these are going to go like this, and this will go like this. So we can actually kind of say that these cancel out. And then the same thing happens here, so this cancels out, and this cancels out, and this one right here, which is going up like that, will have one opposed to it from here, which is going down like that, so they kind of cancel out. Generally, really all you're going to get is, you're going to get this net magnetic field in the minus x direction here, and the plus x direction here, which we'll call hx of x. This is, we can generalize because they really do cancel out quite well, and we actually find later that the height doesn't even matter from how far away it is from the x-axis. It's all the same magnetic field. So to derive it, we're going to do this equation using this integral. So we're going to draw a box around these little loops as such. And now, from the definition of that integral, since the current is coming out, we know that the integral has to follow this direction as such, based on the direction our pointer fingers would point. So we're going to define this length as L, and then this tells us that, I'm going to erase a little bit to make some room. Keep in mind it's ky is equal to negative y. We won't really need that until later. This tells us that, taking the dot product, it's going to be minus L hx of x times the unit vector a of x, which is in the negative direction, which goes over there, dot minus L a of x. Now, really, these are the magnitudes multiplied by cosine of theta, which is really cosine of 0, which is 1, as we all know. That's a 0. Now, this is basically going to turn into L times hx x. This is dl, sorry, so there's no L here, because dl is infinitely small. It's just minus ax. So that way we get L times hx. Yeah. And what would be, yeah, just that. So based on the bottom here, we do the same thing, and since they're in the same direction, you're also going to get HL HXX. So you're going to add that L HXX, and this is equal to I enclosed, as we described before. Now I enclosed is KY is equal to minus Y. My computer just got really loud there. Okay. Now we're going to multiply this by L because it's infinitely long, and we're just taking this cut portion from L. Okay, just making sure it's still recording. Yep, okay. Is equal, stop it. Equal to L times 2 hx of x. L's cancel, so you're going to get, really, let's just say ky is divided by 2 is hx of x. And again, we can tell which direction this is based on the right-hand rule as described before, which directions our fingers curl in. So that is that. That is what we're going to need to know for the problem 7, and it helps us. That whole method that we just did is how you kind of compare the two different calculations, because they're the one like the one half of the plane is in a u naught, and the other one's maybe in like 4 mu naught. So that's how you kind of compare them in the exact same way, looking at that box, the method I just did. Now the other half is is based on another calculation I'm going to go over. It's really just from Maxwell's equations, B dot ds is equal to 0. It's kind of like reminds me a little bit of I mean, how I like to think about it is I think about it a little bit like Gauss's law. It's again kind of like a Maxwell equation, but d dot ds is equal to q enclosed. But I just like to think about, let's say you have like a sphere, and actually I'm not going to do a sphere, I'm going to do a cylinder, and for this one you have a charge inside it, and here it points radially outward. So looking at the ds, they're all in the same direction as where the electric field, or the D field, which is just electric density, is leaving, which means it's going to have a positive value, which means it's going to have a positive Q enclosed, which is correct. So that makes sense. Now, if we look at this is a B field, which is a magnetic field density, actually, kind of like a D field. That's why I'm comparing them. Now in this case, let's imagine that we have a wire with a current coming through it, because this is what produces magnetic field, the movement of charges. Now, in this case, magnetic fields they come back, like they're loops. It's not like they're pointing out in a direction forever. I mean, of course, you could have an infinite plane, which would then produce a general magnetic field in a certain direction, but a wire like this, in this case, you'd have this magnetic field like that, and everything that's leaving enters the sphere again. Now, this is kind of why I like to think about why this holds up logically. That is. Now you have to use this exact same case for what we just derived. Now imagine there's a plane here with all these coming outwards. If we were to draw a sphere like, a cylinder, I'm going to do that like this. Everything that enters exits. So in this case, since the ky is producing a magnetic field that kind of goes over the top and just goes through the side, this is all going to be equal to 0. Now, imagine that we had a different, instead of a ky, like a kz or something like that, or a kx, as defined in the problem 7. Then we look at the top of the sphere and the bottom of the sphere based on how the magnetic field's entering and exiting. And then you could use that based on this previous relationship to calculate what it is that these two magnetic fields are. And we use this whole equation, or not equation, but relationship to to get the answer for that problem and why a certain a certain magnetic field is some number in a different area of the problem. So that is generally all I wanted to show, and hopefully that'll explain some things. Thank you.